Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to look at Newton's method. So in this topic we will describe and derive Newton's method, and this is probably a review from your first year calculus course. We will deduce how quickly the algorithm converges, and consequently we'll be able to describe this algorithm as being order h squared. We're also going to consider situations when this algorithm may not converge. We're going to look at an example of the application of this algorithm. We will then describe automatic differentiation and consider an implementation of this algorithm in C++. Now, suppose that we have a real valued function f of x, which is of a real variable. And suppose that we have a point x sub k that is known to be close to a root. Well, in this case, we could approximate the nonlinear function at the point x sub k by a linear polynomial. That is a first-order Taylor series approximation. That would be that line there. Well, wouldn't the root of that linear polynomial be a better approximation of the root of the original function f of x as opposed to the original approximation x sub k? In all likelihood, yes. So we will designate this next point x sub k plus 1. That will be our next better approximation of the root. And then we can iterate. Now, what is the root of this linear polynomial? Well, we have to find the root of this linear equation. We are solving for x. Let's bring f of x sub k to the right-hand side. All right, so the next thing we can do is we can divide both sides by the derivative at x sub k. All right, now to find the root, all we have to do is bring x sub k to the right-hand side, and this gives us that the root of that linear Taylor series approximation is the point x sub k minus the value of the function at x sub k over the derivative at that point. Consequently, if x sub k is a reasonable approximation of the root, then if x sub k plus 1 is assigned the algebraic expression on the right-hand side, then x sub k plus 1 should be a better approximation of the root. Well, if that's the case, could we not continue? Let us find a Taylor series that passes through that point, find the root of that linear polynomial, and designate that point x sub k plus 2, and so on and so forth, until both our halting conditions are satisfied. That is, the value at x sub k is sufficiently small, and the difference in the step size is also sufficiently small. Now, how much better is this approximation? Well, let us assume that the root is at the point x equals r. And x sub k being an approximation means that the error is r minus x sub k. Well, let's write down the full Taylor series expansion around the point x sub k and determine what it is at the point r, that is the actual root. So we know by the Taylor series that f at r is equal to f at x sub k plus the derivative at x sub k times r minus x sub k plus a half times the second derivative at some point psi between x sub k and r. This is multiplied by r minus x sub k all squared. Well, we know that f at r is equal to 0 because we are assuming that r is a root. All right, easy enough. We can therefore, assuming that the derivative is non-zero at that point, divide both sides by the derivative. So now we're left with this expression here. Well, wait a second. Taking a look at this, we can rewrite this as follows. We can rewrite it as r minus this particular expression plus an expression times r minus x sub k all squared, and that is equal to 0. Consequently, let's bring the expression r minus that expression to the left-hand side, as here, and this is now equal to a ratio times r minus x sub k all squared. Recall that r minus x sub k was the error of the approximation x sub k. Now, let's look at what's in the parentheses on the left-hand side. Isn't that one step of Newton's method? Isn't that the root of the first-order Taylor series passing through the point x sub k, f at x sub k? Actually, it is. And this is our next approximation. So on the left-hand side, we have the error of the next approximation. Consequently, assuming that the first and second derivatives are sufficiently smooth and the first derivative is non-zero, then the error of the next approximation is approximately a constant times the previous error squared. So if the previous error was 0.1, then the error of the next approximation will be a constant times 0.1 squared, or that constant times 0.01. Similarly, if the error was 0.0001, then the next approximation would have a constant times 0.00000001. That seems to be a very fast convergence. Now we are going to describe Newton's method as being order h squared. That is, if h is the error at one step, then the error at the next step will be some constant times h squared. Now, we should ask, will Newton's method always converge? Well, first of all, if there is no root, it certainly is not going to converge. So consider, for example, the function x squared plus 1. This has no root, and consequently Newton's method would iterate forever if it tried to find a root. Also, if the derivative at x sub k is close to 0, the next approximation may be actually much more significantly further away from the root, even to infinity. So, for example, this point may be close to the root, but if we find the first-order Taylor series approximation at this point and find the root of that, that is, apply Newton's method, x sub k plus 1 would be a point significantly further to the right, which would be much further away from the root than x sub k. As an example of Newton's method, let us find the root, or the first root, of 2 times e to the negative 2x minus e to the negative x. All right, now the exact solution is x is equal to ln of 2. However, we're going to start with x sub naught being 0. So that will be our first approximation, and we can see the error of that approximation there. After one iteration, the solution is 1/3, and the error has also reduced. However, let us see what the approximation of the previous error squared times that ratio of the derivatives. All right, so it's estimating that the error with this step should have been 0.5605, but in fact it was 0.3598, which is okay because we actually started a good distance away from the root. So if we iterate again, applying Newton's method to x sub 1, we get this next approximation, and we see that it is now closer to the root. Notice that if we square the previous error and multiply it by that ratio, again, it's estimating that the actual error should have been around closer to 0.1641, but the actual error is within that ballpark. All right, notice that the error is slowly dropping, but not really significantly yet. Let's do one more approximation. Applying this by substituting x sub 2 into the formula, we get x sub 3 is equal to this value. Now the error is reduced to 0.02 and change. The previous error squared times the ratio is actually pretty close. Applying Newton's method one more time, we're getting pretty close to the error. And notice that the previous number squared is pretty close to that. In fact, if we square the previous number and multiply that by that ratio, we get that we're estimating the error should have dropped to 0.0006320, which is actually pretty close to what the actual drop in error was. One more step, notice how accurate that approximation is. That's actually pretty close. And if we square the previous error and multiply by the ratio, that actually is very close to what was expected. Applying Newton's method one more time, the error is now very small, and if we squared the previous error and multiply by that ratio, that's exactly the new error we were expecting. In fact, at this point, if we now apply Newton's method one final time, the actual error is 0. So that is correct to all significant digits after only 7 iterations. Now, in all likelihood, we probably would have stopped much sooner than this, as we were already very close to the root, but we're just iterating now just to demonstrate, for example, how the approximation of the error actually is reflected in the actual new error. Now, for Newton's method to work as efficiently as it does, it requires us to supply both the function that we're attempting to find the root of and its derivative. Now, fortunately, there's actually an algorithm called automatic differentiation that takes a function written in C++ or other languages such as in MATLAB, and it creates a function that gives the value of the derivative exactly. So, for example, in C++, if you gave such an automatic differentiation algorithm the following function, well, it knows how to apply the rules of differentiation to what is being returned. So it says, okay, the derivative of a difference is the difference of the derivatives. It will then differentiate the first expression, which is twice the derivative of the exponential, which is, of course, the exponential times the derivative of the argument, and so on and so forth. So you could actually have a computer algorithm that takes that first function and defines a new function that is the derivative of the function that you originally gave it. And these are defined for most programming languages. So let's have a look at an implementation of Newton's method. we have a number of arguments. First, the function, and the function that defines the derivative of the first function. We have an initial point x0, and we have two constraints, the epsilon step size and the epsilon absolute value. We also, of course, will give it a maximum number of iterations. So in the body of the loop, we will iterate at most max iteration times. If we do not find a solution, we will simply return not a number, a constant defined in the CMath library. The first step we will do is we will calculate the next step in Newton's method, and we will do so by using our initial value, x0. So that's x0 minus f evaluated at x0 divided by the derivative evaluated at x0. Now, just in case this results in something that is not finite, so either not a number or plus or minus infinity, we will simply terminate early and return not a number. We did not find a reasonable approximation. However, if the difference between x0 and x1 is sufficiently small, and if the value of the function in absolute value at x1 is also sufficiently small, then we will return x1 as our best approximation of the root that satisfies the conditions we have. Finally, we simply assign to x0 the value of x1. Note that a parameter can be assigned to just as easily as any local variable because it is simply memory that is allocated on the stack. Following this topic, you now have reviewed Newton's method, which you saw in your first year calculus course. You understand now, however, that the error is order h squared, and we derived this error using the first order Taylor series. You know that the algorithm may not always converge. You've seen an example of the algorithm in practice where it does converge and converges according to order h squared. And you have learned about automatic differentiation and seen an implementation of this algorithm. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!